All right, good morning or afternoon or whenever you choose to watch this. Let's look at the calendar first since things are a little bit changed. Hope your Labor Day weekend was fabulous. Time off, no school. Obviously, I'm out Tuesday and Wednesday, and that's going to change a few things, but we'll still have the test next block day, and we'll still have a couple of review days built in. So we'll be okay to test that day. I'm going to go over lesson 3 right now. We'll do lesson 2 because they're kind of interchangeable. What order you do them in doesn't matter. So we'll do 3 right now. We'll do 2 on Thursday when I get back, and we'll do 4 on Friday, and we won't do that quiz. I might post it so you can use it as a practice, but we won't use the in-class day for that. And that'll get us right back on track by the end of this week. And then next week we'll have some AP type review questions leading into the test. So I don't like being absent, especially 2 days, but canceling a quiz, having an extra review day, and doing one lesson online will be okay. So let's look at the notes page for this is the third notes page, so the one on exponential functions. Exponential functions is y equals e to the x, or y equals 5 to the x, or 3 to the x, or 2 to the x. But let's back up a second. We're going to consider exponential functions. Those are a type of transcendental function. That is not a word you really need to know. Basically, a transcendental function is not a polynomial. So any of the weirder things, the more complex things that we have, those are transcendental functions. So exponential is what we're going to talk about. We've already done trig. We'll do log tomorrow. We'll do inverses the day after that. Those are not algebraic functions. There's a little bit of craziness with them that takes a little special attention. All right, first some exponent properties. This should be old news to you. I hope it is. Power, we can sort of distribute that power, so x to the m, y to the m. If we're multiplying and we have the same base, then I think you can add those. Maybe it's easier if you saw it like that. So this would be x to the m plus n. There's the power root thing. The flower power grows on top and the root grows underneath. So let's see, the power's on top, the root's underneath. We're used to that because we don't like taking derivatives of roots. We like taking derivatives of powers. Power to a power we multiply. X to the 0 is 1. X to the negative 1 is 1 over x. I think we know all of those things. I hope we know all of those things. But none of those are in exponential functions. All of those, x was the base, and a number is the exponent. An exponential function has the variable as the exponent, or as part of the exponent. But the properties still work the same way. So if our x is in the exponent, that's what makes it an exponential function. So we're going to need to be careful about taking the derivative of x to the 5th versus 5 to the x. Those are very different things. That's a polynomial. That's an exponential. Well, let's back up and get some basics down. The graph of what y equals e to the x looks like. If you don't remember, then maybe you do a quick table of values. Let's see, e to the 0 is 1. So that'd be right there. E to the first is e, which is like 2.7 something. Negative 1 would be 1 over 2.7 something, so that'd be down here somewhere. So a rough sketch of e to the x. A couple things we can get from looking at that picture. As x goes to negative infinity, so as x heads off to the left, e to the x, that's our graph, heads to 0. As x goes to positive infinity, e to the x, e to the positive infinity, that goes up to infinity, and it goes up there in a hurry. It gets there very quickly. And then these two things kind of go together. If a limit at infinity equals a constant, then that means there's a horizontal asymptote there. So it has a horizontal asymptote of y equals 0. E to the x is never negative. It's always above the x-axis. E raised to any power is never negative. You can't raise something to a power and end up with a negative number. Right? Like 3 to the negative 1. That doesn't make it negative. That just flips it over. So it stays positive. Always positive. Y equals natural log of x. We'll talk more about tomorrow. They're inverses of e to the x. We'll worry more about that tomorrow. Okay, but now we want to know what the derivative of e to the x is. I don't think I'm going to do this thing on the graph because it's kind of fun to do, because if you look at the graph of e to the x, so if you graph e to the x and you graph the derivative of e to the x, they're exactly the same thing. And so even though this is a really complicated function, it's one of our favorite derivatives to take, because the derivative of e to the x is e to the x, which is kind of nice. And the derivative of e to the u, this is like a chain rule thing, is e to the u, but then don't forget u prime, that's the chain rule off the top there. So we really like this derivative because it's the easiest one. It doesn't change anything other than don't forget the chain rule. Tootsie Roll Pops. Okay, well, that's pretty easy. If our base is not e, then let's see. Well, let's jump to the answer. This is a lot of work to get to the conclusion, so we can just bypass all that and jump to the answer here. So these are the ones we just did. The derivative of e to the x is e to the x. Derivative of e to the u is e to the u times u prime. But if we have a different number, a different base, so if we have 3 or 4 or 7, then it works pretty similarly. So it's still a to the x, but we have to multiply by the natural log of whatever the base is. You can kind of see that that's true here as well, but if you multiply by the natural log of e, that's 1, and that's why we don't ever write that, because it's not necessary. But it wouldn't be wrong. So if you wanted to remember one rule, you could just remember this rule. Actually, you'd remember the next rule. A to the x, a to the u, natural log of a times u prime. So the natural log of a, because our base is not e, u prime for the chain rule. So you absolutely, absolutely must know these rules. But truly, if you wanted to get by with just memorizing one of them, you could memorize the most complicated one, and that covers all the rest of them. So if A is E, then this just devolves into this one. And if U is X, then it devolves into this one. So that's the full one. If you memorize that one, you've got them all covered. But most people basically memorize these two, because usually there's a chain rule involved. So don't forget the chain rule, and then don't forget this extra natural log if the base is not e. All right. Please do not use the power rule on exponential functions. Power rule works for algebraic functions. So let's do a little demonstration here. So the derivative of x to the 5th, that would be 5x to the 4th. We know that. The derivative of 5 to the x, okay, that's not a power rule thing, because this is an exponential, not a power rule. This is 5 to the x times natural log 5. So those two are easy when we're thinking about them separately, but when we throw them in together, or when you haven't thought about either one of them in a while, and we throw one of them at you, sometimes people get them reversed. All right, some example problems. Find the instantaneous rate of change, I rock, meaning derivative. Take the derivative of e to the 4x cubed when x is 1/2. So dy dx, that's the same thing as instantaneous rate of change. That's the derivative. Again, we love taking derivatives of e to stuff because it's the same thing. E to the 4x cubed. Except you can't forget that there's a chain rule that still applies. The derivative of the top thing would be 12x squared. So that's dy dx, but we do want to evaluate that at 1/2. So e to the 4 times 1/8, if I cube 1/2, times 12 times 1/4, because 1/2 squared is 1/4. That would be a safe stop, but we've got multiple choice. We need to clean this up a little bit. 12 divided by 4 is 3, and 4/8 is 1/2. So 3e to the 1/2. That's the same thing as 3 times the square root of e, but I should have looked at my answer choices first. There's 3e to the 1/2. So that's a long notes, but it's an easy process. Keep the thing and don't forget the chain rule. Oh, here's some more quick derivatives here. Derivative of e to the x is e to the x. Derivative of e to the 2x is e to the 2x times 2. Why don't you press pause right here and see if you can get the next 4 real quick. So press pause right now and then we'll come back and look. Alright, e to the 5x times 5, e to the negative x times negative 1. Chain rule. Of course, we'd probably write that a little bit differently, like that. E to the negative 2/3 x times negative 2/3. E to the negative x over 2 times negative 1/2. So it seems to be too good to be true, maybe. It's not hard, it's just the chain rule that you've got to remember to add on to that. And then we start mixing it in with other things. So this looks like a quotient rule about to happen. Find the slope of the line tangent to, okay, so that's the derivative in terms of x. So this is another one of those f and g problems. The top will be f, the bottom will be g. F prime then is e to the 2x times 2, and I'm just going to put the 2 in front because it looks better there. G prime is the same thing, e to the 2x times 2. And now I'm ready to use the quotient rule, gf prime minus fg prime over g squared. Right? The gf has to come first. That's the only way the chain rule works, among other things. The gf has got to go first. So g is e to the 2x plus 1 times f prime, 2e to the 2x, minus f e to the 2x minus 1, parentheses here to make sure that minus sign goes all the places it needs to go, g prime, 2e to the 2x, all over g squared, e to the 2x plus 1 squared. Alright, that's probably a lot of simplifying that can go on. I start looking at my answer choices. They all have g squared, so that doesn't really help. It looks like it's all about what's in the numerator here. So this is calculus is over. Now it's algebra time. If I distribute, that would be 2e to the 4x plus 2e to the 2x minus 2e to the 4x plus 2e to the 2x. I'm not going to write the denominator again because I know what it is. It can't be simplified. It's already over in all the answer choices, so I'm really just worried about the top here. The e to the 4x's will cancel, and that gives me 4e to the 2x in the numerator. So I go look at my answer choices, and that is answer choice A. Number 4 is product rule, so this should go quick. Let's see, f prime is 1, g prime is e to the x. Some people aren't writing out the product rule stuff, other people are writing it out. It's fine either way. So f g prime plus g f prime. Perfectly acceptable answer, but none of my answer choices look like that because I can factor out an e to the x and get answer choice C. Number 5. We'll skip number 6 when we get there. Find dy dx. So there's a 3 there, but it still works the same way. 3 to the 4x squared. Chain rule times 8x. And then, because the base was 3, we got to do times natural log of 3. So let's see if we got all of that somewhere. I think that's the same as answer choice A. They've got them in a little bit different order, but it's multiplication, so that doesn't matter. So answer choice A. Number 6 we don't know how to do yet because of the natural log, so I'll hold off on that one. Number 7. So h prime then is e to the f times g times chain rule, but chain rule is going to involve the product rule, fg prime plus gf prime. And that's all at x equals 6. So f of 6 is 1, g of 6 is 6. So it should be e to the 6, but they've all got that. F of 6 is 1. G prime of 6, so that's the slope there. That looks like 1/2. G of 6 is 6. F prime of 6, that's the slope of f at 6 is -1. So that's e to the 6th times 1/2 minus 6. So that's 1/2 minus 12/2 is -11/2. So D. So that involved the new rule, chain rule, product rule, and getting it from a graph. So I had a little bit of everything in there. All right, so your assignment is worksheet 3. We'll cover worksheet 2 tomorrow. So we're a little bit out of order, but I think this was an easier one to follow if I'm not there. So hope you enjoyed the video or at least learned something from this video. Obviously, I'm available for tutoring on Thursday during B-Lunch if we still have questions. Plus, we'll have time to go over some of this stuff in class. So sorry about missing. Look forward to being back with you, and I hope the video was helpful.